Let's continue our history lesson with Ernest Rutherford, a physicist from New Zealand, and his very famous gold foil experiment. Here's the experimental setup. So there's a radioactive source over here. You recall it was Becquerel who just recently discovered natural radiation. This particular source, when it decays, when it disintegrates, is giving off alpha particles. Remember, those are tiny little bits of positively charged matter, which we now know to be helium nuclei. They've lost their electrons. And these alpha particles move very, very fast. They're very, very tiny. They move fast. They have a positive charge. And he's shooting these alpha particles, directing them at a very thin foil of gold. Now, I never really found out why it was gold. Maybe the budget was large for his experiments, and they were able to afford gold, but more than likely it's because gold has a pretty heavy nucleus. And this gold foil was hammered till it was ridiculously thin, really only a few atoms thick, thinner than any piece of aluminum foil you could imagine. And then the idea is that these alpha particles are so small they should be able to pass through the gold foil, which you get a sense of the size of the gold atom. That's what Rutherford was trying to discover. And he put a detector screen here so that anytime an alpha particle hit, the detector screen would light up. Now, he expected most of these alpha particles to go straight through, but here's where he got very, very smart. He figured it might happen. Some of these alpha particles would get deflected at larger angles. So he made the detector screen go all the way around, so it would capture the hits from any sort of alpha particles going off at any sort of angles. All right, we're going to watch a little bit of video from YouTube to describe what happened in the experiment.
Later in the experiment. Now, based on J.J. Thomson's model, Rutherford developed a hypothesis. Thomson said the atom was spherical and had uniform density with these little negative flecks called electrons throughout it. So, Rutherford's hypothesis was that when he bombarded a sheet of gold atoms with alpha particles, 99% of them should go straight through that uniformly dense, positive fluffiness of the atom. And every once in a while, he'd see some outliers on the X-ray film hitting just outside to the left or right because they might get deflected just slightly by those little negative electrons.
Okay, so let's break this down. Here's the plum pudding model of the atom that Thomson proposed, where the positive charge is spread all throughout. That's this sort of pinky stuff, and the electrons are sort of suspended here. Remember, there were the plums and the plum pudding, and he's shooting the alpha particles in. Here's the detector screen on the other side. Remember, the alpha particles are tiny, they're moving very fast, and they're positively charged. The idea is that the positive charge is sort of diffused all throughout the atom and not concentrated. There's no way that it's going to interact very strongly with these positively charged alpha particles. It's only the electrons that could possibly cause this to be deflected. So here's it going through. This dashed line is the original direction it's moving, and it passes by an electron, gets deflected, passes by an electron, gets deflected, and comes out the other side, almost in the same line from which it started. Here was the original line, here it gets deflected by a tiny bit, here's another alpha particle, it goes through really quickly, gets deflected a little bit, deflected a little bit, deflected a little bit, maybe comes out a little bit farther away. But really, he's expecting most of these to go straight through, or really, maybe with tiny, tiny deflections one way or the other.
So this is what Rutherford expected to see based on Thomson's model. His experimental results were different. Yes, 99% of those alpha particles went straight through. Every once in a while, one was slightly deflected. But what he also noticed was that he was getting hits on the X-ray film at severe angles, meaning some of these alpha particles were being deflected even straight back at the alpha emitter.
Wait, what? That shouldn't happen at all. These alpha particles are going so fast, and they shouldn't be interacting with this diffuse positive charge. They should only be deflected at tiny, tiny angles, and yet some of them were going at these huge angles off to the side, and some of them were coming right back towards the source. Rutherford was so aghast at this, so surprised with this. Here's his very famous quote. "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper, and it came back and hit you." Let's try to put that in perspective. A shell is like a bullet or a missile, really. 15 inches, in this case, the diameter of that. This is a 15-inch shell, to put it in perspective. This is a 15-inch shell. Imagine firing it at a piece of tissue paper. It should, of course, just rip right through. And he's saying, what if you fire this huge missile at a piece of tissue paper and it comes back and hits you? This is completely unexpected. There is no way this should possibly happen.
This led him to two conclusions. First, 99% of the alpha particles went straight through. That's his first observation. Leads to his first conclusion. Most of the atom is empty space. His second observation is that the particles that don't pass straight through are deflected at severe angles, some even straight back at the alpha emitter. That leads him to a second conclusion, that there must be something dense at the center of the atom, almost like a post that these alpha particles are hitting. And the second part of that second conclusion was that even the particles that made it straight through and weren't deflected at severe angles had the pathway altered. They were bent away from this dense core. They were repelled by that dense core. So, in total, here's what he observed. 1, most of the alpha particles pass straight through. Conclusion, most of the atom is empty space. Observation 2, the alpha particles that didn't pass straight through were either repelled or deflected at severe angles. Conclusion 2, the atom has a dense, positive core.
Okay, here is a Phet simulation that'll help you visualize it from one more perspective. So this is the Plum pudding model again. These tiny blue dots, they're the electrons, they're the plums suspended. The orangey reddish cloud here, that's the positive charge all spread throughout. And we're going to shoot the alpha particles with a lot of energy through. And you can see that the vast majority of them go straight through. In fact, I think all of them go straight through. This is the detector screen over here. That means they're all going to show the hits on the detector screen in straight lines from where they started. Because the positive charge of the alpha particle can't interact with the positive charge of the cloudiness here because it's all spread out. It's not localized anywhere. We switch over to the Rutherford atom. This new picture of the nuclear atom. And again, I'm going to increase the alpha particle energy. Let's see the traces here. Here are the alpha particles. And you can see a lot of them are still going relatively straight through until they get close to this nucleus, this dense core of positive charge. And that's where they go through these large deflections. Look at that. Right? Still, a lot of them are going pretty much straight through, or almost straight through. It's only when they get close to it they have these large deflections. And this is so surprising, so new. Here's a picture that's a little bit closer to what you just saw in the YouTube video. More of these dense nuclei. And here, when it hits has almost direct hit or a direct hit, that's when they go off with these very large angles. But still, a lot of them are going straight through. All this comes together for his Rutherford's conclusions. When they did this experiment, they expected pretty much all these alpha particles to go straight through. And that is what happened. It was like 99.9% that went straight through. It's really just like, it was like 1 in 20,000 that didn't. So we got to really visualize what's happening here. Rutherford figured out this experiment. He didn't actually carry out the experiment. He got 2 helpers to do it. Geiger and Marsden. Geiger you may have heard of. He eventually invented the Geiger counter for detecting radiation. So these 2 graduate assistants were doing the actual experiment. When you're in graduate school, you'll do pretty much anything to get your name on a paper, to get noticed by anyone at all, right? So these 2 guys, they were doing the experiment, and the whole experiment probably was set up on maybe like a lab station like you might have in our classroom. It was a relatively small experiment, and they were shooting the alpha particles in, and they had to watch these little lights flashing on the detector screen, which means they had to turn the lights off, and the whole thing was relatively small, so they'd be looking through a microscope, and they'd be looking for hours on end, days, weeks, months collecting data. And out of all the data they got, 1 in 20,000 experiments actually produced something that was interesting. That was the 1 in 20,000 where the alpha particle went off at a very large angle, creating a hit on the detector screen, totally unexpected. And so the first conclusion Rutherford drew from this was that if the vast majority of these particles are still going straight through, 99.9% of them are still going straight through, that means they're not hitting anything, which means the atom must be mostly empty space. Nothing. There's literally nothing there. Right? So when we draw pictures of the atom, they're not even close to being to scale. The distance between the nucleus and the first ring of electrons is a tremendous space on the atomic scale. It's mostly nothing there, absolutely nothing. Which means that you, you're composed of atoms, you are mostly empty space. You're mostly empty. Doesn't mean you're bad people. It's just that if we were to condense you down with everything sort of touching, you would probably fit in the palm of my hand. Right? There's so much nothingness in you, making you have a larger volume. Okay, so the vast majority of them went straight through, mostly empty space. But then, when 1 in 20,000 hits something, that means that, well, what they hit, if the alpha particles are positively charged, they must have gotten deflected by the positive charge. They must be localized. So here's his second conclusion. That most of the matter and all that positive charge must be located in the center of the atom, which he now deemed the nucleus. And then I say he has a third conclusion, because the electrons had to go somewhere, so the electrons couldn't be all spread throughout, otherwise the alpha particles would have some weak interactions with them. They must be somewhere else. They must be on the outside. So we sort of changed the model, pushing electrons to the outside, drawing all the positive charge into the middle, right? So we changed the model. Here's Thomson's model. We push the positive charge all the way to the middle, the dense core, the nucleus, push the electrons to the outside, and they're zipping around. This is what's now known. Oh, sorry. And then later, just a couple years later, is when Rutherford finally found the proton. It wasn't just a big collection of positive charge, the nucleus. These were made of individual particles as well. And so now here is his model, which we call the planetary model for kind of obvious reasons. I mean, look, it looks like, planets orbiting a dense star or something like that, right? So here's the positive charge all drawn to the middle, the negative charge on the outside. The negative charge must be in motion, though, because it's got to provide some sort of structure, right? Dalton's original model of the atom was that billiard ball, so it seems like there's like a defined edge to it. That can only happen if the electrons are moving around very, very rapidly. So rapidly they seem to create sort of a shell, even though it's not really what's happening, but that sort of defines the outer edge of the atom. Alright, so then we get to 1913, Niels Bohr. And Niels Bohr said, wait a second, there's a problem with Rutherford's model. Let's look at this in a little more detail. Here's Rutherford's model again. Here's the electrons zipping around in circles. What could possibly be wrong? We got electrons, which are negative charges, and they're going in circles. And circular motion is accelerated motion. So here we have electric charges that are accelerating. What happens when electric charges accelerate? Oh, right. They emit radiation. They lose energy, right? That's where electromagnetic radiation comes from. And so if they are going to emit radiation, they should be losing their kinetic energy, and every single one of these electrons should spiral in, and the whole atom should collapse. So that sounds like a problem, doesn't it? Right? And this should have happened eons ago. We shouldn't even be here to talk about it. So Bohr said, hey, there's a problem here. These electrons should be losing energy. So how did he fix it? He said, electrons don't lose energy. Well, he said a little bit more than that, but that's kind of what he said. At this level right now, that's what he said. Here's what he really said. He said, the electrons can only occupy orbits of certain radii, certain distances away from the nucleus, and if they're in these orbits, they won't lose energy, because they can't lose energy. They don't lose energy. They definitely don't. Otherwise, we would have collapsed, right? So there's got to be something that's causing them not to lose energy. We'll get into more detail about this in next class. But here's Bohr's new model, right? So on your paper, you have the two orbits. That's what's drawn on your paper. Let's draw the nucleus. And just for simplicity's sake, let's just put 6 protons in the nucleus, because that's easier than the, I think, 13 I had in the previous picture. So we know there has to be 6 electrons. And accompanying this, there are restrictions on how many electrons can be in any individual orbit. In the first orbit, there can only be 2 electrons. The remaining 4 are in the next orbit, or what we call the energy level, sometimes even called shells. And of course, they're still in motion. And now we're getting much closer to the model of the atom that we are used to.